Today is such an exciting day. I can barely contain my happiness and excitement and enthusiasm for the subject we're going to start today. Laplace transforms. Now, I'm generally super excited about math in so many different ways. Physics, engineering, math. I love them all. But Laplace transforms, I've got to say, is one of those special things. And I wish that I can unlearn Laplace transforms so that I can experience the thrill of learning it again for the very first time. That is the degree to which I hold Laplace transforms. And if you are watching this and you don't know Laplace transforms, I'm so envious and I am jealous that you get to learn it. And I'm happy that I may possibly be the one to teach you all about Laplace transforms. It is such an honor to be the person who will teach you about Laplace transforms. It is that powerful of an idea. Let me just write down the basic gist, the idea, the concept behind Laplace transforms and how we can use it to solve differential equations. And it is one of those disruptive ideas. It's not those plus epsilons on existing techniques like exponentials and little tiny epsilons here and there. This is one of those disruptive, earth-shattering techniques that totally changes the way you think about differential equations and actually the way you think about math in general. So let's write down the idea behind this extremely powerful concept. Let me explain this disruptive idea of the Laplace transforms. Step one is, let's suppose you have a differential equation that is a little hard to solve. Maybe not just a little, but really hard to solve. The idea is we're going to take that problem, which is really hard to solve, a differential equation that you can't quite solve, and blast it. Send it over to another space, whatever that means. We're going to send it to another space, and then in that space, that problem that was really hard over there is suddenly really easy to solve. Okay, step two is now that you're in this space, we're going to solve it in this easier dimension or easier space. And then step three, take that solution, blast it back into the real dimension, to the real space, the world that we live in, and then boom, out comes your answer. It kind of it sounds like I'm explaining Star Wars or something, like some miraculous thing. I'm not narrating the plot of Star Wars. This is an actual thing. It's an actual mathematical technique. And it's amazing. And I can't wait to explain it more to you. But let me just first explain more of the concepts, graphically, what we're about to do. And with that, you'll be able to put into context a little bit later on what we're doing with Laplace transforms. Let me just draw a quick picture of what we are doing. Let's graphically draw what we're talking about. We have some kind of function, a function you want, temperature profile, height profile, concentration profile, any function that you want to solve from a differential equation. And that's got variables in real space or real dimensions like time, position x, y, z, usually time with Laplace transforms. So let's just stick with time. So time is something you can feel and count, right? That's a real space variable. We're going to take that variable, blast it into a new space, and we're going to transform it into a new variable called s, the letter s, and we're going to solve the problem over here where the equation became easier. So the first step is we're going to transform the problem from real space to a new space. So we've transformed using Laplace techniques to go from a real space variable over to a variable s in this new dimension or new space, whatever that is. And what's remarkable about this technique is that the result is you can take an equation that was hard to solve, for example, like an ODE, and that really hard ODE magically turns into an algebraic equation. You guys would all agree that solving an algebra problem is much easier than solving an ordinary differential equation. And it would be insane if we can really take an ODE and convert it into an algebraic equation. It just seems like magic, black magic. That is what I call Laplace transforms, black magic. It's just so remarkable how well it works. It just seems impossible that you can take an ODE and convert it into an algebraic equation. That's what Laplace transforms would do. It's black magic. In fact, it's not limited to ODEs. You can also do it for PDEs. If you take a partial differential equation, take the Laplace transform, it will downgrade it into an ODE. So essentially, what Laplace transforms would do is it would take a really hard equation to solve in real space, downgrade it by one level. It takes a PDE to an ODE, which is much easier to solve. You take an ODE to algebra. Okay? And just so that you know, this type of technique to transform an existing variable or space that you're in to another variable or dimension or space is a fairly common technique. Laplace transform is kind of like the first magical one that you'll learn, but there are other techniques. We'll cover another one in this class called Fourier transform. That's another very common technique that's used to take a really hard equation, convert it into a much easier one to solve. There are many others, like Hilbert transforms that you can convert into Hilbert space. There are an entire family of techniques to convert an existing problem into a different dimension that's easier to solve. And then once you solve the solution over here in this new space, you can transform it back into the real space. Just like that. The idea is we're going to take a problem, send it over to this new space, solve it there where it's easier to solve, invert it back to this real space dimension. So we're going to take an indirect route and then get at our solution. All right. So there are a couple of different ways in which Laplace transforms is very useful. And it's used across all areas of science and engineering. But let me just jot down a couple of ways in which it is specifically useful for solving many engineering applications. It is useful, for example, for solving coupled or a system of ordinary differential equations. In science and engineering, that is so common to have a system of equations. You might be able to couple a heat transfer equation with a species mass transfer and chemical reaction equation with a fluid flow equation. Those three equations might all be coupled to each other. So you get a coupled ordinary differential equation. If you get that, then using Laplace transforms will allow you to downgrade a coupled ODE into a coupled algebraic equation. And a coupled algebraic equation is, of course, much easier to solve. Another case in which Laplace transform is super useful is when you have to solve a non-homogeneous differential equation where your right-hand side term g of x is weird. Remember that tree diagram I made? And there was that one case over here on the middle right-hand side where I said, if your g of x term is weird, then Laplace transform does an amazing job. So weird functions might involve functions that are, for example, could be discontinuous, periodic, piecewise. It could have jumps and pulses. It could have steps. And those are the situations where Laplace transform becomes very useful. And there are lots of situations like that in science and engineering. Suppose you're building a reactor. You have some kind of reactants turning to products. And you're dumping in some kind of new reactant C into the reactor. And how you would explain that mathematically is say, I have a reactor going. It's got equations of motion that describe how the reaction is proceeding. And at some time t, maybe 10 minutes later, I want to start dumping in a third component, concentration C, or species C, into the reactor. That would be kind of like a pulse or a step function happening at time t equal to 10 minutes. And that type of mathematical description of a physical process becomes very hard to solve when you don't have Laplace transforms. But with Laplace transform, that kind of discrete process, like a step, like, oh, I started adding a chemical reactant C at some time t, at 10 minutes, boom, I start adding it. And the equations are able to handle that kind of discontinuous piecewise step in your concentration profile. And that's really hard to solve when you don't know Laplace transforms. But with this kind of technique, it's able to handle those kind of weird situations and weird cases that actually happen a lot in science and engineering. Okay, enough of all this intro and calling it black magic and all these things. Let's start getting into the details. What is a Laplace transform? What is it about? Show me a differential equation. Show me, prove to me what this can do. Okay, I hear you. Let's go into the details of what is the definition of a Laplace transform and how might it be useful for solving differential equations, and what kind of properties does it have? Let's get started. Suppose we had a function, little f, as a function of time t. And that function, little f of t, satisfies the ordinary differential equation shown here on the upper left. Just your standard generic second order ODE with constant coefficients and a right-hand side g as some function of time t. Now, I'm going to define the Laplace transform of the function little f. Let's see what it looks like. The definition of the Laplace transform, which has a script curvy L, that's the mark for an operation of the Laplace transform, operating on this function little f of t, which is a function you want to find, is defined as the integral of time t integrated from 0 all the way to infinity. So imagine you're taking this integral from 0 time all the way out to infinite time. And the integrand is kind of interesting. It's got the function little f of t, which is the function you want to ultimately obtain, but it multiplies against this weird exponential term, e to the negative st, where s is some new variable, a new space that we're in, variable s, times t, the time that you know, you and I know, and you take this integrand and you evaluate it from 0 to infinity. This is the definition of the Laplace transform of some function little f as some function of time t. Now, this is standard notation. This type of integral in Laplace domain is called capital F of the function s. And the reason why we've written it this way is that if you look at this integral, we are integrating over all time. It's a definite integral with respect to time, which means that time is no longer in the problem at all. It's disappeared. And all we're left with is some function of the variable s, right? S is the only variable left over after performing this integral. And therefore, it's written over here as some other function, capital F, of the variable s. To be clear, capital F is not a function of time anymore. Time is gone. Let's write that down. So once again, this is a definite integral with respect to time t. So the answer of this integral does not have time t in it anymore. So the time t was swapped in the form of this exponential with a new variable s. So remember up here, I wrote that we're going to blast our solution into a new space where t is gone and swapped with a new variable s? Here it is. So let's draw that figure once again. We've taken this real space variable of time and the function you want, which is little f as a function of time, and we've done a Laplace transform to ultimately produce another function, capital F of little s, over in the Laplace domain, or S space. And if we can go from one direction, from a real space, time, to an S space, we can also go back from S space back to real space, where this time we would perform an inverse Laplace transform of the capital F as some function of S back to the real space domain. So this is Laplace forward transform, inverse transform. So you're either dealing with a real space variable, little f as a function of time, or you're in this other dimension, this new space S, where you have another function, capital F, as some function of little s. Now let's define the inverse transform. OK, so here is the definition of the inverse transform of the function capital F of s back to the function you want, which is little f as some function of time. Disgusting. Oh my gosh. It's got complex imaginary numbers I, which is square root of -1. It's got poles, gamma minus and plus I infinity are poles. Oh my gosh. I infinity, doesn't it make you nauseous just looking at it? It makes me nauseous. And you take another integrand, capital F of s, multiply it with e to the positive st this time, integrate over all s. And so this is how you swap back from the variable s back to the real-time domain and get back the function you want. Now, this looks crazy. We're not going to do this in this class, so you don't have to worry about it. But this is the proper definition. So it turns out that it involves a lot of complex integrals for you to invert back from the S space back to real space. So there's an entire class on complex analysis and doing contour integrals in the complex plane. That's the kind of thing we would need to do a proper inverse back to the real space. And there's a technique called the method of residues to do that. But in this class, we're not going to do inverses in this way. There are lots of forward and inverse transformed pairs that are conveniently calculated. And we're going to do a couple of them by hand as well. And there's enough critical mass of those tabulated values that are actually very useful for most problems in science and engineering. So we're going to take that approach and not do this formal inverse transform. So you don't have to worry anything about what I've written here. It's just I'm showing you the proper definition. Things can get pretty complicated pretty quickly, but we're going to do a different approach for converting it back from the solution that we have in capital F back to the real time domain, little f of t. So with that, let's get started with a couple of the properties of Laplace transforms and how those functions might behave. And then eventually, we'll be able to solve differential equations, invert it back into the real space without doing any of this nauseous thing, and get back the answer that we ultimately want to go off and solve really important and hard problems in engineering. So let's get started with some of the properties of this Laplace variable. Let's move on to a couple of key properties of Laplace transform variables. First, question. Does every function little f of time t have a Laplace transform? Can you take any function, take its Laplace transform, and expect a well-defined Laplace variable? No, but most functions do. So not every function has a Laplace transform, but most do. And the general rule of thumb where a Laplace transform exists is when your function is continuous by sections and it doesn't diverge for some finite t. Let's write that down. So one of the criteria for a function to have a Laplace transform is that the function you want, little f of t, is continuous by sections. And I'll draw a picture to show what I mean by that. Suppose I have some function that is defined between these two bounds, but then at this point it jumps, and this is a discontinuous jump to a lower value, and then it keeps going. So this is sectionally continuous. This is totally fine. It has a Laplace transform. A situation where it does not have a Laplace transform is if it diverges at some finite time t. Let's also draw a picture of that. So here's an example of a function where a Laplace transform does not exist. This is tangent of x, or tangent of t, some independent variable. It diverges at, right, pi over 2 and negative pi over 2. Therefore, because it diverges to infinity at some finite time, it does not have a well-defined Laplace transform. Laplace transform of tangent does not exist. But up here, where it's sectionally continuous, that's OK. This function has a Laplace transform. Okay? So as long as you are sectionally continuous, it doesn't diverge out to infinity at some finite time, then you have the chance of having a Laplace transform. Now let's go to the second criteria. The second criteria is that the function you want, little f of t, must be of exponential order. Now what do we mean by that? If we go back to the definition of the Laplace transform, you see that we basically take the function you want, slap it with e to the negative st dt, and then integrate under the curve of 0 all the way to infinite time. So the function you want, little f of t, cannot get bigger faster than this exponential, e to the negative st, drops. That's a little confusing, so let me just write that point down. So this thing, the function you want, cannot get bigger faster than e to the negative st gets smaller. Sorry, it sounds like a Dr. Seuss puzzle sentence, but let me just give you some examples to mean what I'm talking about. OK, I just wrote two quick examples. First one is the Laplace transform of e to the t, that exists. Because when you take e to the t, plug it into here, you have e to the t, which explodes exponentially in time, right? E to the t explodes, but e to the negative st decays. And it decays quickly enough such that the product of one function that explodes and another function that decays is such that this integral is well-defined. You'll get a well-defined integral that comes out. In contrast, the second example, Laplace transform of e to the t squared does not exist. And the reason why it does not exist is because if you put e to the t to the squared into this integral, this function, t squared, is going to grow faster than this linear drop of negative st. Therefore, the product of e to the t squared times e to the negative st will be growing as a function of time. Try to perform this integral. If you try to take e to the t squared, multiply it by e to the negative a constant times t, integrate from 0 to infinity, you'll get infinity. Because the area under the curve is just going to diverge out to infinity. So the function you want can't grow bigger, faster, compared to this thing that you're multiplying is dampening your function. I hope you get that. It's kind of a subtle point, but it has to do with the convergence of your integral. It basically says you need to be able to perform this integral. If this integral gives you infinity, you're not making any progress. So you must be able to perform this integral that gives you some finite value. And to do that, your function cannot get bigger faster than the thing that you're multiplying and slapping it with. Okay, that's criterion number 2. Let's move on to our next property of Laplace transforms. The Laplace operator is a linear operator. What do we mean by that? Suppose you wanted to take the Laplace transform of the following term. Some constant a times the function f of t plus b, another constant, times a different function of t, g of t. Now, what we mean by a linear operator is we can see what happens to the fate of a and b when you work through a little bit of algebra. So, when in doubt, always use the definition of the Laplace transform. So let's apply the definition in this case and see what happens. All I wrote here is everything inside the bracket times slapped on an e to the negative st, integral from 0 all the way to infinity. Right? This is just applying the definition. Replace the function f of t with a more complicated form of the function that it's applying the Laplace transform on, but otherwise you just use the straightforward definition. Now, just from straightforward calculus, you know that we can separate the sum of an integrand into an integral of sums. Just like that. So I've just divided a single integral into a sum of two different integrals. But at this stage, you know that this constant a can pop outside the integral because it's just a constant. And you know from calculus that a constant inside the integrand can just come outside. Same with this b term over here on the right-hand side. Therefore, this is nothing more than the sum of two Laplace transforms. Just like that. So this is what we mean by a linear operator. If you have some operator operating on a sum of two separate terms, each multiplied by a constant out in front, it is nothing more than the constant a times the Laplace transform of f plus another constant b times the Laplace transform of g. So it just linearly operates on each term, and constants out in front can just pop outside like you would expect for any linear operation. Okay, so with this definition and this property in mind, let's evaluate a very simple Laplace transform and actually use this linear operator approach to extend that result by a little bit. So let's do a small example. Suppose I wanted you to evaluate the Laplace transform of 1, the function 1. It's a constant for all time t, but it is a valid function. What would the Laplace transform of 1 look like? When in doubt, use the definition. You just plug in your function into the integral, slap on an e to the negative st, integrate from 0 to infinity. Let's try that. So I've taken the function 1, put inside the integrand, multiplied with e to the negative st, integrate from 0 to infinity. This is just standard definition of a Laplace transform. Now, this integral is very straightforward because s is a constant with respect to this integral, so we can just evaluate the integral of an exponential. Just like that. So all I did was took the integral of e to the negative st. You get negative 1 over s, e to the negative st, with a lower and upper bound of 0 and infinity. Now, when you evaluate the upper bound, e to the negative st vanishes because t is going out to infinity, which means that e to the negative infinity is 0, minus the lower bound, where e to the 0 is equal to 1. And therefore, this term inside the brackets becomes negative 1, cancels the negative outside, and all you're left with is a 1 over s. So apparently, the Laplace transform of the function 1 is equal to 1 over s. Kind of an interesting result. And therefore, you can do the simple extension of this result using the linear operator property. The Laplace transform of a constant a, therefore, using this property, a is a constant, f of t is equal to 1, and we know what the Laplace transform of 1 is. We just determined that it's 1 over s. So all you need to do is to multiply a times the Laplace transform of 1, which is 1 over s, and you get your answer. It is simply equal to a divided by s. So for some of you who've worked with Simulink in the past, for example, in your control or process control class and feedback class, on the block diagram on Simulink, there's a diagram. Whenever you want to do an integral, there's a little box that says 1 over s on it. It kind of looks like this. There's a little box with lines coming into and out of that box, and inside that box it says 1 over s. It means an integral. And because everything on Simulink is performed in the Laplace domain, the block symbol for an integral is just 1 over s. And now you know why. Because the Laplace transform of some input signal coming into a block is just simply equal to 1 over s. And so it all comes back to Laplace transforms. And using a Laplace transform of a, using the linear operator property, is just a constant out in front times 1 over s, which is the Laplace transform of the function 1. Okay, one more little trick, mathematical trick that you can use to figure out little tiny operations of Laplace transforms. So let's move on to a small little trick, which is kind of like a corollary of what we were talking about right here. All right, let's suppose we wanted to take the Laplace transform of the function you want, f, but the argument inside the function of f is multiplied by a constant a. So as opposed to a times the function, we have the function argument a times t. Now, this Laplace transform is commonly called the change of variables. So once again, to figure out where the fate of a ultimately goes in the Laplace transform version, let's use the definition. When in doubt, use the definition. We slap this function f of argument a times t with an e to the negative st, integrate from 0 to infinity. Now, we can do a small little change of variables to simplify or rewrite this expression just like the following. All right, I did a small substitution where I let a new variable tau take the form of the constant a times t. So it's kind of like a stretched time axis, where I've taken normal time, stretched it by a factor a, just a change of variables like you would do in calculus. And so if you take the small increment dt, because we want to replace all the time up here with tau, dt is just equal to 1 over a times d tau. So we could plug in dt into this differential element, which gives you directly d tau over a. The bounds of your integral doesn't change because time t equals 0, tau is 0, at infinity, tau is also infinity. So the bounds don't need to change. And the inside, the integrand, f just becomes f of tau, because that's how we defined our function tau, or variable tau. And our e to the negative st now becomes e to the negative s over a times tau, because our t is tau over a. So we have a factor of tau over a inside the exponential. Just a change of variables. But now, when you actually stare at this new expression, remember that t or tau are just dummy variables with respect to the integral, because we're ultimately integrating from 0 to infinity. So if you look at this integral, we have some function f of tau, e to the negative s tau, d tau, and we're integrating over 0 to infinity. So this can be written in the following way. Just like this. So first of all, the 1 over a inside the small differential can be outside the integral because it's a constant, so you get that 1 over a. Now, this is the part that's a little bit tricky, but let me explain it. So we have the function little f of tau times e to the some argument negative tau integral over d tau. Therefore, if you go back to the original definition, this integral was some function f of little t e to the negative st dt, and we said that this thing was equal to f of s. And that s came from the exponential prefactor to time. Just like that. So then, if s is some other variable, s prime, then this would just also become s prime. Therefore, the argument in the exponential is just s over a, and therefore it just becomes capital F s over a. Easy as that. So what you would need to do is to evaluate your Laplace transform of little f, which is your capital F, and then plug into that expression s over a. We'll do an example a little bit later on that demonstrates how you would plug in a different variable other than s. We'll get to that in a little bit. But this is how it's handled. So whenever you have a function that you want, where the argument is a constant times time, it just appears as a 1 over constant pop outside, and then the Laplace transform of little f, but the argument is s over a. Again, we'll see that in a little bit. But here are the first two properties of Laplace transform. Let's keep going and discuss a couple more. I wanted to finish with just two more properties. And these two properties of Laplace transforms are very important. These two are called the shifting properties. There's two of them. The first shifting property considers what happens when you have the function you want, little f of t, is multiplied with an e to the at. How do you take the Laplace transform of that product? Like we've been doing, when in doubt, use the definition. I'm just using the definition. I've taken the integrand f of t. I've put in e to the at, but I've written in a way where I combine the two exponentials. We usually slap on an e to the negative st. That's right here, e to the negative st. I've combined them so that I've written it as negative s minus a times t. And now, as you just saw with the change of variables, we have a pretty similar situation where we have f of t, e to the some quantity times t, integral from 0 to infinity. So this is nothing more than the following. It is just capital F, the Laplace transform of the function you want, a little f, but shifted by a factor a in the S space. Kind of interesting, right? So you have the function you want multiplied with e to the at. In the Laplace domain, how it manifests is a shift along the axis, but along the axis of the S space. This is called the first shifting property. Let's do a brief example so you can see how this shifting property works. Suppose we wanted to evaluate the Laplace transform of e to the at. I've written times 1 there, but you can just omit that. It's just Laplace transform of e to the at. Okay? And now with the first shifting property, this is extremely easy to evaluate. I don't even need to use the definition really anymore, because this is written like above, e to the at times some function of t. In this case, it's just a function, a constant equal to 1. So according to this shifting property, this is just equal to capital F S minus A. According to the first shifting property, this is what it's equal to. But we know what capital F is. We just did an example earlier. We just found earlier that Laplace transform of 1 is equal to 1 over s. You saw that. You're convinced because I used the definition and I showed you that Laplace transform of 1 is equal to 1 over s. And this is our capital F, right? That's the definition. This is the Laplace transform, capital F of s, of the little f of t, which is 1. Therefore, all we need to do, moving back to the left, is shift this function by a. Let's do that. Just like this. So all I've done is to take the capital F of s, which you already know the solution of, is 1 over s, and substitute the argument with s minus a. So I've just plugged in this 1 over s with the argument s minus a. And that's it. So the Laplace transform of e to the at times the function 1 is just equal to 1 over s minus a. You can see that in this derivation or solution, I didn't use the definition anymore. I just took our pre-existing knowledge that the function 1 has a Laplace transform 1 over s, and I just plugged in s minus a. So I shifted the s space by a factor s minus a. That's it. So the shifting property is extremely easy if you already know what the Laplace transform is, and you just build on top of that by shifting by a factor of a. That's it. That's the first shifting property. And I'll show you how this is useful in science and engineering and also useful for solving differential equation in a bit. But for now, let's move on to the second shifting property. Let's now talk about the second shifting property. But before we get into that, I'd like to first introduce a Heaviside step function, which is kind of an interesting function. You may not have heard it before, but we're going to need the Heaviside step function to introduce the second shifting property. But also as an aside, the Heaviside step function is a very important function in science and engineering. Let me just define what this function does first. It's denoted oftentimes by the capital letter H. Sometimes it's defined as the Greek symbol theta, sometimes by other letters, but all you need to know, I'm going to use h all the time, but all you need to know about this function is that when you have an argument time t minus a, some constant, the Heaviside step function jumps from the value of 0 to the value of 1. And it does this jump discontinuously at the value equal to t of a. Let me graph this function and show you what it looks like. All right, so the Heaviside step function is this odd function, odd as in not even and odd, but just unusual function, where the time t dictates where the jump occurs, and the constant a is exactly where the jump occurs. So it has a value of 0 for all values less than a. So it goes along this axis for all values less than a. And at exactly a, it jumps to a value equal to 1. Just like that. So that's why it's called a step function, because it's 0, 0, 0, 0, 0, 0, 0, 0, 0, boom, step to a value of 1, 1, 1, 1, 1, 1, 1, 1, all the way. And some of you might be wondering, what happens exactly at a? You can see the bounds were less than or greater than a. At exactly a, defined by a half. In most numerical solvers, if you evaluate the Heaviside step function exactly at the jump, you'll get a half, which is exactly the value in between those two values. But it's not really well defined at the jump. It's all the way 0, and then boom, steps to 1. Okay, that's really all you need to worry about for now. Okay, so the reason why this function is very important is because in science and engineering, it's often used to turn functions on and off. Let's multiply this Heaviside step function by the function you want, and you can see how the function gets turned on or turned off. So if I were to take this function, Heaviside of t minus a, take the function you want, f of t minus a, then what this function does is it turns on the function exactly at the value of a. Before a, it's always equal to 0 because you're multiplying the function you want with 0, 0, 0, 0, 0. So it's 0 all the way, but precisely the value of a, boom, the Heaviside jumps to 1, and therefore all you get is the function to come out. So it's basically a switching function. You can imagine how that might be important. If you're building a heat jacket to prevent a certain electrical component in your system from overheating, you want to activate the water coolant inlet into your heat jacket at a particular time. And it might be once a certain temperature is reached inside your electrical element, I want to start the inflow of coolant into the heat jacket. And therefore, T minus A would be the exact moment that temperature is reached, beyond which maybe it'll start to destroy your system. You don't want that to happen, so you set an upper tolerance for your temperature. And then you want your flow rate, F of t, to start pumping in coolant. And so you want it to be 0 all the way because you don't want to waste energy. You don't want to pump in unnecessary coolant into your system. So it's 0 all the way. But at some time t equal to a, boom, the coolant entry starts. Okay, so it's 0, 0, 0, boom, you've started the inflow of your coolant. This is the context in which a step function might be used to keep a function off for a set period of time. In a certain condition, boom, you want to turn it on, and you want to turn it on perpetually. Okay? You can also turn off functions. Suppose you take this and subtract it at a different time, t minus c. Then you turned it on at a, but at time c, boom, you can shut it off again. So you can turn it on or shut it off. That's what the Heaviside step function will do for us. And you'll see how this is applied for problems later. Now, with the knowledge of the Heaviside step function and what it does to the function you want, let's start getting to the second shifting property. which is first asking, what is the Laplace transform of this quantity? This function, turn on, turn off. You take the Laplace transform of that process. What is it equal to? Once again, let's use the definition. Just like that. I've taken the term inside the Laplace operator, put it inside the integral, slapped on an e to the negative st, integrate from 0 to infinity. Now, we have to start massaging this equation so that we can make sense of it. First, you know that this integrand will be 0 for all time t less than a, and bigger than a, it's going to turn on to the function little f of the argument little t minus a. So all we're going to do is to split this integral into two terms like we can always do when doing integrals. So I've split the integral into two, one going from 0 to a. In that case, as you saw here, from 0 to a, this whole heavy side is equal to 0. And therefore, the integrand is just equal to 0 plus another integral going from a to infinity. And in this integral, the heavy side is equal to 1. And therefore, it just leaves the function on ft minus a, and then still the e to the negative st integrated from a all the way out to infinity. Now, all we need to do is first recognize this term is 0, and all we need to do is think about the term on the right. Let's do a small change of variables to see what this integral on the right gives us. I've made a small change of variables where I've let a new variable tau equal to t minus a, and then d tau is just simply equal to dt. Therefore, first, the bounds of the integral becomes 0 to infinity, no longer a to infinity, because we have taken the t, shifted it back to the origin, and so now for the perspective of tau, it is going from 0 to infinity. First term, f of the argument tau now, simply because we've replaced t minus a with the new variable tau. Inside the integral, e to the negative s, again, I've replaced t with tau plus a, and so simply I just swapped out the t with tau. And lastly, the differential d tau. Now, just one more step and we're all done. We're actually going to pull out e to the negative sa from this integral, pop it outside because it's not a function of tau. It's just a constant that can be pulled outside the integral. Just like that, I've pulled out e to the negative sa outside this integral, and we're just left with that term on the right. And you've seen this enough times for you to recognize that this is the definition of the Laplace transform of little f. Tau is just a dummy variable. You can swap it with little t if you want. And now the connection's exactly clear. This is nothing more than the Laplace transform of little f, also equal to capital F of s. So this is the second shifting property. Let's write it down cleanly over here on the left. There we go. So the Laplace transform of this heaviside function multiplied against the function you want, when it's shifted in real time by a factor of a, then all it is for the Laplace transform of little f, which is capital F of s, times e to the negative as. So if you compare the second shifting property with the first shifting property, you start to see some comparisons between them. In the first shifting property, you're multiplying in the real space by a factor of e to the at, and then out comes a shift in the Laplace domain by a factor of a. In contrast, the second shifting property multiplies in the Laplace domain by a factor of e to the negative as, and then out comes in real space a shift by time t equal to a. Let me write that down and graphically illustrate this. All right, so we now have the first shifting property boxed in pink. That's the one you need to remember. And then the second shifting property also boxed in pink. Those are the two expressions you need to remember. Now, in the real space, what we found is that when you multiply by e to the at, boom, you shift in the Laplace domain by a factor a. Second shifting property, when you shift in time by t minus a, in the Laplace domain, you multiply by e to the negative as. So what you can see is that the first shifting property and the second shifting property do and undo each other. You can clearly see that there is a parallel between them. That's the most important thing to remember, aside from each of these properties itself. So in conclusion, the first and second shifting properties do and undo each other. So that's enough properties for us to all gather. This board is full, and I feel like we're getting a little bit tired going over properties. It's important to remember properties, because if you don't know what the property of a Laplace is, you can't really apply for differential equations. In the next lecture, we're actually going to start applying Laplace transform. Finally, after all these definitions, properties, we're going to apply it to Laplace transforms. And that's where you're going to see the magic of how do you go from an ODE to an algebraic equation. You should be excited for the next lecture. See you next time.